Whenever devices are connected in parallel, they have to have the same potential difference as one another. So in this case, where a capacitor and an inductor are connected in parallel with one another, they have to have the same voltage at any instant in time. The voltage across a capacitor is just charge divided by capacitance, and the voltage across an inductor is negative inductance multiplied by the rate of change of current. But then again, rate of change of current is the second derivative of charge with respect to time. Well, if we solve a differential equation of this form, we end up showing that the charge on the capacitor oscillates sinusoidally according to this expression. So a graph of the charge on the upper plate of the capacitor is just a graph in the shape of a cosine curve. Charge versus time oscillates sinusoidally. The maximum and minimum values for the charge, negative Q and positive Q, that maximum amount of charge is just equal to CE. That's what you get when you throw the switch into position A and allow the upper plate to become positively charged to an initial value equal to the product of the capacitance and the battery voltage. And that's just as well to call it capital Q in place of lowercase q naught. When we throw the switch into position B, that electric field that had built up between the plates of the capacitor when the switch was in position A starts to decrease. The electric field shrinks as this clockwise current starts to develop in the circuit. That clockwise current flows through the inductor, and as the electric field is shrinking, the magnetic field in the inductor is increasing. So let's take into account some energy considerations. Not only can we equate voltages, but we should be able to equate energies by the law of conservation of energy. I want you to think of a swinging pendulum. When the pendulum is released from this point, the energy is potential. When it reaches its lowest point, the energy is all kinetic. And when it swings through half of a cycle, the energy is all back to potential again. Of course, it's going to swing back to the equilibrium position where the energy is once again kinetic. So let's consider a point somewhere in between where the energy is a combination of potential and kinetic. That total amount of energy has to equal the initial maximum potential energy, or the maximum amount of kinetic energy has to be every bit the same as the maximum amount of potential energy. The way in which the charge oscillates on the capacitor is somewhat like the way in which a bowling ball oscillates when swinging as a pendulum. Let's see. At some point, right when the switch is first thrown into position B, the energy is all in the capacitor, and energy in the capacitor at its maximum value is equal to the maximum charge squared divided by 2C. Now, if it's not the maximum value, then the energy in the capacitor is lowercase q squared over 2C if the charge has started to become a little bit less as the current flows through the inductor. Energy in the inductor, maximum energy in the inductor, is 1/2 L capital I squared. If it's not the maximum value, then it's 1/2 L lowercase I squared. So we can imagine a point in time where some of the electric field has collapsed. We've gotten toward not the maximum magnetic field, but a little bit of magnetic field has developed in the inductor, and the current has not reached its maximum value yet. So let's see. We could say that the maximum value of the energy in the capacitor has been transformed into a combination of some energy in the capacitor plus some energy in the inductor. In other words, capital Q squared over 2C, the maximum initial energy in the capacitor, is equal to lowercase q squared over 2c plus 1/2 L I squared. Let's multiply through by 2 so we can cancel that out in every term. And then we get Li squared is equal to 1 over c times the quantity capital Q squared minus lowercase q squared. Or I squared is equal to 1 over LC times capital Q squared minus lowercase q squared. So the amount of current at any instant in time is equal to the square root of 1 over LC times the square root of maximum charge squared minus instantaneous charge squared. That reminds me of something. In our study of mechanics, we found if we put a mass on a spring and pull that mass back, give it some amplitude, in other words, a displacement from its equilibrium point, when we release it, it oscillates. So two types of oscillatory behavior, electrical oscillation and mechanical oscillation. And for the mechanical oscillator, we said the maximum energy, which is the energy you put in it right before you release it, that would be 1/2 K amplitude squared. When the mass on the spring is at some point halfway between full amplitude and the equilibrium position, then it has a combination of potential energy 1/2 K x squared plus kinetic energy 1/2 M V squared. And in this equation, we can also multiply through by 2 to get us an expression that says mv squared is equal to K times the quantity a squared minus x squared. You see where we're going with this? If we divide both sides of the equation by m and take the square root of both sides of the equation, we get v is the square root of k over m times the square root of a squared minus x squared. Notice the similarity in these two equations. We've suggested before that we can make a comparison between a capacitor and a spring. When a spring has no mass attached to it, it sits at its equilibrium position, and when we attach some mass, then the spring sits at a lower position, and there's only a force in that spring when there is some displacement, and the force is equal to kx. There's a voltage across a capacitor as long as there's some charge on its plates, and that voltage is equal to Q over C, or we could say V is equal to 1 over C times Q. We've also argued that a resistor is a device that only has a voltage if there's a rate of change of charge, or in other words, if there's a current flowing through it. Current, after all, is dq dt, and the voltage is equal to IR, or RI. That's sort of like a coffee filter falling through the air has a force of air resistance equal to BV. So it looks like that X is to Q as spring constant is to the inverse of capacitance, and velocity is to current as drag coefficient is to resistance. Oh, and inductors are devices that only have a voltage across them if there's a rate of change of current, and that's sort of like a heavy object at rest. When a force is applied, it accelerates, and that force is proportional to the acceleration, but then again, acceleration is dv dt. So mass is to inductance what rate of change of speed is to rate of change of current. So The analogous quantity for mass is inductance. The analogous quantity for spring stiffness is the inverse of capacitance, and the analogous quantity for drag coefficient is resistance. In the same way that the analogous quantity for position is charge, for velocity is current, and for acceleration is rate of change of electrical current. So now do you see, if we take this equation for the mechanical oscillator that says velocity is equal to the square root of k over m times the square root of amplitude squared minus instantaneous position squared, and replace it with all of its analogous quantities, then analogous to velocity is current, analogous to mass is inductance, analogous to spring stiffness is the inverse of the capacitance, analogous to amplitude is maximum charge, and the analog to position is instantaneous charge. And so by just replacing analogous quantities in an equation you're probably familiar with from your study of mechanics, we can derive an equation that applies to the behavior of this oscillating circuit. Now, what's the maximum amount of current? Well, the maximum amount of current would then be equal to, well, you get the maximum current at the moment that the capacitor is totally discharged. So, again, if the switch had moved into position A, we've started out with the maximum amount of electric field and zero magnetic field. And then we throw the switch into position B, and a little bit of the electric field goes away. And that's due to the fact that some of the charge on the positive plate has leaked off as a current flows in a clockwise direction. That current flowing in a clockwise direction makes a little bit of magnetic field appear in the inductor. Eventually, the electric field in the capacitor equals zero when the charge on its plates is equal to zero. At that moment in time, the current has reached its maximum value, and the magnetic field in the inductor has reached its maximum value. And so the energy in the capacitor is zero, and the energy in the inductor has now reached its maximum value. And this behavior cycles back and forth. The loss of magnetic field becomes an increase. Actually, the electric field after half a cycle will point the opposite direction in the capacitor, and then the energy in the inductor is equal to zero, and the energy is all back in the capacitor equal to Q squared over 2C. So the maximum amount of current is when the charge on the capacitor is equal to zero. So if we let the charge on the capacitor go to zero, then we're really just taking the square root of capital Q squared, which just gives us Q, and so maximum current should be equal to 1 over the square root of LC times capital Q. Now, keep in mind, the charge on the capacitor is varying in time according to the equation. Q equals CE cosine omega t. Q equals CE cosine omega t. Well, current is just the derivative of charge with respect to time. So this is negative omega CE sine omega t. And a graph of current versus time then looks like a graph of negative sine. There's a minimum and maximum value. And of course, the maximum you ever get from this part of the expression is 1. And so the maximum current should be equal to omega times c times epsilon. Now, do these two expressions agree with one another? Well, let's see. Let's make a substitution for EMF and omega. So I maximum is equal to, let's see, omega is the square root of 1 over LC. Got it. And we've got to incorporate the C. Got it. And then we need to substitute for E. Well, let's see. When the switch was first put into position A, then the maximum amount of charge is equal to C times EMF. So when we rearrange that equation, we could say the EMF is equal to maximum charge over capacitance. So how about that? Maximum charge over capacitance. Oh, well then if we just cancel out these C's, then we get, indeed, I max is equal to the square root of 1 over LC times Q. Yeah, these two expressions do perfectly agree with one another. So just a little insight into the energy considerations of the oscillating LC circuit and how that behavior is analogous to a mechanical oscillator made of a mass vibrating on a spring.